Have you ever noticed how certain things seem to move together? When weather gets hotter, ice cream sales go up. When advertising budget rise, website visits increase. Or maybe you have seen that students who study more tend to score higher. These are all examples of relationships, patterns where two things appear connected. But appearance can be deceiving. Are these connections real? Are they strong or weak? And can we actually measure how much one variable moves with another? That's exactly where correlation analysis comes in, one of the most essential tools in statistics and data science. In data analysis, understanding how variables relate to each other is at heart of discovering insights because most real-world decisions depend not on one number but on how things move together. Welcome back to Shital's Data Days, your one-stop destination for turning complex data concepts into clear, real-world insights. In today's video, we will learn what correlation really means, different types of correlation, how to interpret correlation coefficient R, how to visualize relationship with scatter plots, difference between correlation and causation, real-world examples in business, finance, and healthcare, and some common mistakes to avoid. By the end, you will not only understand correlation, you will know how to use it to uncover patterns and make smarter data driven decisions. So, let's start with basics. What exactly is correlation? In simplest terms, correlation measures how two variables move together. When one variable changes, does the other tend to change too? And if so, in which direction? If two variables increase or decrease together, like height and weight or income and spending, we call that a positive correlation. If one goes up while other goes down, like screen time and sleep quality, that's negative correlation. And if there's no consistent pattern, variables are said to have no correlation. Correlation helps us go beyond isolated data points. It shows us how things are connected, whether strongly, weakly, or not at all. For example, when we study temperature and ice cream sales, we might notice that as temperature rises, ice cream sales also rise. That is clear positive relationship. But correlation doesn't tell us why. It only tells us that movement happens together. In data analysis, this idea of moving together is central. It helps business scientists and analysts uncover meaningful relationships that guide predictions, decisions, and deeper investigations. Simply put, correlation is a language of relationships in data. It tells us whether two variables dance in sync, move in opposite direction, or stay completely independent of each other. Before we dive deeper, let's take a moment to understand logic behind correlation. At its core, correlation measures how two variables move together, whether their values rise and fall in sync or in opposite direction. Behind the scene, correlation is built on something called covariance, a way of checking how each variable's deviation from its mean line up with other. If they tend to deviate in same direction, covariance is positive. In opposite direction, it is negative. We then standardize that covariance by dividing product of standard deviation of both variables so that measure becomes unit free and always lies between -1 to +1, and that gives us correlation coefficient, often written as R. R of +1 means both variables move perfectly together. -1 means they move in perfect opposite direction. And 0 means no consistent linear relationship at all. In simple terms, correlation is just a way to quantify how two things vary together, giving us clear comparable measure of their relationship. Let's look at different types of correlation, which help us understand how variables may relate based on direction, strength, and form. A positive correlation means both variables move in same direction. As one goes up, other tend to go up too. Negative correlation means they move in opposite direction. One goes up, other goes down. Strength refers to how closely two variables move together. When points on scatter plot form tight line, that's strong correlation. When they are loosely scattered, correlation is moderate or weak. Most commonly, we consider linear relationships, where changes happen at consistent rate. But sometimes relationships are non-linear, curved or in complex form. And in those cases, standard correlation may underrepresent true relationship. Together, direction, strength, and form help analysts understand not just if two things are related, but how they move together. Now that we have seen types of correlation, let's focus on the number that quantifies it. Correlation coefficient R. R ranges from -1 to +1. When R is equals to plus 1, it is perfect positive correlation. As one variable increases, other increases in perfect sync. When R equals to minus 1, it is perfect negative correlation. As one variable goes up, other goes down in exact proportion. When R equal to 0, it means no linear correlation. Variables move independent. Closer R to plus 1 or minus 1 means stronger relationship, and closer it is to 0 means weaker relationship. From technical point of view, most common version we use is Pearson correlation coefficient, which measures strength of linear relationship between two numerical variables. Formula is R equals to covariance of x and y divided by product of standard deviation of x and y. What matters here is understanding that R tells us how consistently two variables move together and in which direction. So to summarize, R ranges from minus 1 to plus 1. Sign shows direction of relationship. Magnitude shows strength of relationship. And R only captures linear relationship. Curved or more complex patterns require other tools. So far, we have talked about Pearson correlation, which measures linear relationship when changes happen at steady rate. But what if relationship is curved or your data isn't normally distributed? That's where rank-based correlations come in. Spearman's row and Kendall's taw. Instead of comparing raw values, they compare ranks. How high or low each value sits in order. This lets them detect monotonic relationship, where one variable generally increases as other increases, even if pattern isn't perfectly straight. In simple terms, Pearson looks for linear relationship. Spearman and Kendall look for ordered relationship. So, when your data is non-linear, has outliers, or uses ranks, these methods tell story more accurately. Now that we know what correlation coefficient tells us, whether it's Pearson, Spearman, or Kendall, let's learn how to interpret it, both in terms of strength and direction. Direction of correlation tells us how two variables move in relation to each other. Positive value means both variables increase or decrease together. Negative value means one increases while other decreases. Value near zero means no consistent linear pattern. Then there is strength. Closer R to plus 1 or minus 1 means stronger relationship. Closer it is to 0 means weaker relationship. Analysts often use rough guidelines. Values between 0 and plus minus zero point 0.3 are considered weak, plus minus zero point 0.3 to plus minus zero point 0.7 moderate, and above plus minus zero point 0.7 strong. But remember, context matters. Zero point 0.4 correlation might be meaningful in social sciences, but same value could be considered weak in engineering. So keep in mind, sign shows direction, magnitude shows strength, and context tells you how important that strength really is. Now that we know how to measure and interpret correlation, let's talk about one of the biggest misunderstanding in statistics, difference between correlation and causation. Just because two things are correlated doesn't mean one causes the other. Correlation only tells us they move together. It doesn't tell us why. For example, ice cream sales and drowning incidents both increases in summer. They are correlated, but one doesn't cause the other. Real reason is the third factor, temperature. That is what we call a spurious correlation. To claim causation, we need more than correlation. We need experimental evidence, logical reasoning, time based patterns, or controlled conditions. In analysis, we must always ask what else could be influencing both variables? Which variable is the driver? Are there lurking factors? So remember, correlation suggests, causation confirms. Being clear about this distinction is what separates a good analyst from a great one. Let's bring correlation to life with real world example, followed by two quick illustrations across other domains. Imagine you are an analyst at an e-commerce company. Your marketing team wants to know whether increasing ad spend actually leads to higher sales. You collect 6 months of daily ad spend and revenue data. When you plot data, you notice clear upward trend. You calculate R equals to plus 0.85. That is strong positive correlation, confirming higher ad spend is closely associated with higher sales. This insight helps justify marketing budget decision and forecasting. Now to quick examples. In healthcare, researchers study physical activity versus cholesterol and find R equal to minus 0.60. That is moderate negative correlation. As exercise increases, cholesterol tend to decrease. In finance, analysts measure correlation between two stocks. If R is close to plus 1, they move together. Less diversification benefit. If R is near 0 or negative, they move independently, helping risk management. These examples show how correlation is used across industries to discover relationships, identify opportunities, and guide smarter data driven decisions. But always remember, correlation is just a starting point. It shows patterns. What you do next matters. Even though correlation analysis is simple in concept, it is surprisingly easy to misinterpret. Let's go over a few common mistakes and how to avoid them. Mistake 1: confusing correlation with causation. Just because two things move together doesn't mean one causes the other. Mistake 2: ignoring nonlinear relationship. Pearson's are major linear association. So if relationship is curved, correlation may underrepresent it. Mistake 3: focusing solely on statistical strength without context. A strong correlation might look impressive but may not be meaningful in real life. For that, ask, is it actionable? Mistake 4: using small or biased samples. With limited data, correlation results can be unreliable. Larger, representative sample lead to more robust insight. Mistake 5: data dredging or p hacking. Running multiple tests until strong correlation appears. That inflates false positives. To avoid these pitfalls, visualize your data first. Check for linearity and outliers. Consider sample size and always interpret correlation in the context of real world meaning. Doing so ensures your analysis is not only statistically sound but also relevant, ethical, and insightful. So, to wrap up, correlation analysis helps us understand how variables move together. It tells us whether relationships exist, how strong they are, and in what direction they go. We explored what correlation really means, different types, positive, negative, and zero, how to calculate and interpret correlation coefficient, and how to distinguish correlation from causation. We also looked at real world examples and common mistakes analysts must avoid so that your conclusions stay reliable and meaningful. Remember, correlation doesn't prove cause and effect, but it is powerful first step in uncovering relationship that can lead to deeper insights, better models, and smarter decisions. If you found this video helpful, make sure to like, share, and subscribe to Shital's Data Desk, where we simplify data one concept at a time. In our next video, we will go beyond relationships and learn how to apply statistics for real world analysis. Get ready for applied statistics for data analysis, turning theory into insight. Because knowing method is one thing, but using them to tell powerful stories through data is where real impact begins. Thanks for watching.